Okay, it's now 11:45 my Eastern time, and this is 1645 European time, or UT. So we have two talks in this session, one by Sarah Markoff and the other one by Matt Lister. First is Sarah. Sarah got her PhD at the University of Arizona, working mostly on the galactic center. She then, during her postdoc time, she then expanded to include X-ray binaries and has made a lot of insights into both the galactic center and the X-ray binaries. She's now the professor of theoretical high energy astrophysics at the University of Amsterdam in Holland. And she's also chair of the EHT's multi-wavelength working group. So I'll go back into my black hole and leave it to Sarah to.
Okay, great. Well, thanks a lot, Alan. And I didn't realize you were going to go back as far as my PhD. Anyway, so it's been really great. Thanks a lot to the organizers for inviting me. I've really enjoyed the talk so far, and especially hearing so much from people outside, the sort of EHT collaboration sphere who are interested in the potential of ngEHT. My talk's a bit of a continuation of what we've been hearing today and a bit yesterday, but I'm going to be focusing a little more specifically on what we can gain by combining our EHT images and hopefully also movies and ngEHT with multi-wavelength and potentially even multi-messenger facilities. And I'll say a bit more about what I mean by that, but also how this might impact the way we think about the observing campaigns. And I should say that this talk is a bit of a mix of different hats, because I'm speaking on behalf of the multi-wavelength working group, which is something I co-coordinate with Kazuhiro Hada and Daryl Haggard. But also there'll be some mention of my research group, including many of the people you've been hearing talks from before. In orange are always the young people, past and present, and then other collaborators who've also been speaking quite recently. And of course, the famous Kaushik Chatterjee will be finally giving his talk in the next session. So you'll finally get to hear a little more about his direct work. Okay, so it's interesting that, hold on, I'm gonna hide my panel. Oops, that was the wrong one. I wanted to hide the floating thing so I can see my slides. Okay, sorry. So, it's interesting that we've known about supermassive black holes in AGN for decades, and yet we still get stuck on many of the same questions. And you've been hearing about this throughout the meeting. I'll just reframe this a little bit for this talk. But to my mind, one of the main questions is, what exactly does this inner 100 gravitational radii around an accreting black hole look like? And we know that there's a lot of this dynamical motion and plasmas, and this is really where the central engine and all the action is happening, and the gravitational potential energy that comes in from the fuel, is converted into these other forms, including these jets that we're so interested in that can span up to size scales of millions to billions of the place where they're basically launched. And this is a really interesting region that we'd like to understand, but the point is that we can't actually see this with any, even the most perfect telescope, because basically any wavelength that we look at will end up basically picking out a particular part of the system. And in fact, what's interesting is that the light that we actually see, of course, is due to tiny particle motions, much smaller than the system, where they're being kicked up and gaining energy. Somehow all these dynamical motions are trickling down to things like turbulence and shear and instabilities. And we've heard quite a lot about this also this morning from Sasha, but this big gap in scale makes it difficult to do everything at once. And what this translates into in some sense is a kind of layer of uncertainty between what we see and the interpretation, a unique interpretation, I would say, of what's going on in this central engine. And now if we start to take a step outwards, and think about what this engine is launching, we run into these questions that have been around for a long time. Alan Marsh, of course, our moderator, has been very involved in this. And what's going on with these very large-scale jets? How are they being collimated? The pressure balance obviously must be, holding them together. Is that coming from the outside medium or magnetic fields? And there's a particular question that I'm really interested in that relates to particle acceleration and ties into this question also of potentially multi-messenger, now that we know that, or we think that many of these neutrino sources are blazars. And that is that if all of this sort of dissipation and shear and instabilities are happening along this jet, as you would think, why is it that when you look at many blazars, and this is a spectrum of very typical sort of bright blazar Parks 2155, you can fit the entire spectrum over 15 orders of magnitude, basically with a single ball of plasma localized, in this case, somewhere around 1,000 gravitational radii down the jet from the black hole. So something, special is maybe happening there. And if we can understand what's driving this region, my mouse just died, interesting. Oh no, there it comes back. I'm having technical problems. I didn't have it all, of course, when I tried to set up. But basically then, the question is what's driving this? And if we can understand the connection between what happens in these outer jet regions and the patterns that come from the central engine by combining these horizon scale images with what's going on further out, we get a lot more information. And of course, multi-scale systems like this, by definition, are multi-wavelength. And so, no matter how great ngEHT is going to be, we're not going to solve these problems by looking at a single frequency, which is just picking out some band down here. We need to combine with information from other frequencies. And of course, also, this is very dynamical. So as you've been hearing throughout this meeting, we really want to aim to capture movies and variability. So that's kind of the scope in which I'm going to be talking. And I want to just first mention, before I go to ngEHT, this question about the how did multi-wavelength play a role in the EHT work that we've done so far. So I'll briefly talk about that. You've seen many of these images, so I probably don't have to go into too much detail, but the key point is that we can take these underlying GR-MHD workhorse models that we use and set them up with different magnetic configurations like SANE and MAD, different types of spin going from all the way retrograde to all the way prograde. And then we take a choice of some kind of electron prescription to kick these electrons up to higher energy. And then we see that, we can have radically different sources with different mass black holes. And then the mix of this, I believe we agreed n equals 0 order and n equals 1 and above, gets all blurred together into the same more or less image that's indistinguishable. And so this uncertainty in being able to uniquely backtrack to what's going on was actually dominant. It was contributed about 10% to our ability to really constrain the mass and therefore test, for instance, the charometric prediction. But of course, we're interested in breaking this degeneracy for many other reasons. And where multi-wavelength becomes really important is because once we make a choice in this R high or any of the other prescriptions you use, we're locking in the electron distribution. And then those same electrons will also go on to radiate from infrared to potentially the gamma rays via synchrotron and inverse Compton. And so what we'd like to do is take all that information from the multi-wavelength and then try to break this degeneracy and improve our models. So that's where a lot of the work is going at the moment. And in fact, we did this to some extent in the original papers. So you can go back and look at our first series of 6 papers in 2019. But this goes back to the points that, for instance, Roger said on the first day, which is we can use constraints from multi-wavelength to already rule out some of these model space. And one of these constraints is the power of the large-scale jets that are being launched from M87. And from various multi-wavelength constraints, especially from the X-ray, but also other frequencies, we see these large lobes that are being inflated on the largest scale by the jets feeding into them. So there's something like calorimeters basically adding up all the energy. The problem is this is integrated over quite a long time, so it's not necessarily a good representation of what the source is doing today, but it's a pretty, gives us a sense of the upper limit. However, if we measure all the light that's coming out of the jet at the same time that we look at M87 with EHT, then we have a very good constraint. In fact, we did that. I'll be coming back to talking about this really amazing campaign that we ran in the multi-wavelength. But what we did was we took all the light from that and we found that at the moment that we looked in 2017, basically the entire system was giving off about 10 to the 42 ergs per second. So what we can say is that the jet as a minimum has to be, basically has this much power, because usually probably it has hundreds of times more. And then we can compare that to the power in the jets in our simulations and decide whether or not we can rule some of them out based on this constraint. And so if you look at paper 5, we actually have this interesting rejection table for these models where you see, things like all the underlying models, the SANE versus MAD and the spin and the R high, these parameters that were the figures I just showed, and then different tests for pass fail. And most of the models that could be ruled out were ruled out based on this jet power requirement. So you can see that many of the ones that passed the others failed here and then led to a total fail. Now, what's interesting is none of the models, sane or mad, with spin equals 0, actually could pass. Now, we didn't go as far as claiming that this was some kind of proof of the Blanford-Zanaev enhancement you might expect from a spinning black hole powering the jets, but it's an interesting point. And I want to add to that something for the people here who are interested in exotic compact objects, because so far, a lot of that work has been focusing on, maybe trying to reproduce the image with a depression. But you have to remember that these multi-wavelength constraints apply to everybody, including, weird black hole mimickers. And so if you have something exotic there instead of a black hole, you also have to have a mechanism to launch jets that we already are kind of struggling to get the power from, even with a spinning black hole. So I think that that's an interesting point. Sorry, my voice is a little hinky. But then we also looked at, for instance, we had a column here about the X-ray luminosity. And what we did was we mainly made this as a kind of hard limit. And we said, okay, if any of these models with this prescription go radically over this, then we ruled them out. It really only ruled out a few models. But now, especially within the theoretical groups, the theory and simulation working group, a lot of us are working on trying to model the entire spectrum that we took during this campaign, because that's really the golden constraint and can rule out many more models, as well as trying to expand the parameter space of sanes versus MADS configurations, but also many more complicated prescriptions, as you've been hearing in several of the prior talks. And so that's where the multi-wavelength campaign comes in, because we exist as a working group to ensure that these data sets exist for testing the models, to know what the source was doing at the time we look at the HT. And so we organized these campaigns in 2017, also 2018, we're organizing them, now. And we've seen this image before, but it's very important because, of course, we know that this is a multi-wavelength emitter. And this paper is just about to be resubmitted, and it should be in press pretty soon. So we're really excited on behalf of this working group and all these external partners that this is actually the first time we've been able to show these results at a conference. But Daryl flashed this in her talk yesterday. But this is a sort of timeline of the multi-wavelength campaign. So we've got the ngEHT campaign on M87 here over about a week. And then you can see that we have radio all the way up to gamma ray coverage, and it's quite long, quite concentrated here. And this is the sort of golden constraint SED. So this is basically what we think was coming out of M87 at the time that we looked. And what you see again, as I put this into about 10 to the 42 here, shows you the power coming out is about 10 to the 42 ergs per second total. And then this is in frequency. And so one of the first questions we'd like to understand is, can you really explain this similar to a blazar? Does it look like most of the energy is coming out, at least the high energy things like the gamma rays and potentially neutrinos, from one region? And so the naive thing that you might want to do is try out one of these single zone models. We didn't go into a lot of detail in the modeling in the paper because we wanted to make this more or less heuristic and focus on the data. The other thing is all of the data I want to emphasize is, are going to be available on a repository. So you can download them and you can take your favorite model, and I hope you will, and try to test it out versus this. But you could think, well, okay, so if we're really interested in the region, this is stratified, optically thick emission from the jets. So if we pick the region that's bounded, by the ngEHT observations, this is the light emitted within about 7 gravitational radii, we can make a single zone, and we can, first of all, know that the fact that the source goes optically thin somewhere above 86 gigahertz, or we wouldn't have been able to see the shadow, likely even higher, restricts the magnetic field to being milligauss. And then having that already is one of the 3 variables we need to pin down the synchrotron. So then we can make a fit to the synchrotron where we have some sort of, thermal Maxwellian and maybe a little non-thermal tail. This is just heuristic. This isn't like a real model at this point. And then you can ask, okay, so what would we need to, for instance, fit the rest of the spectrum, the gamma rays, if we had SSC? So we could kick this up. If the particles have an energy around 10 to the 5, 10 to the 6, the leptons on average, then you could do this energetically. But this pins down another synchrotron constraint, which then means that you need about something like 10 to the 5 you need about 10 to the 8 particles in this region to be able to have the optical, enough optical depth to scattering. So basically getting a lot of scattering to push this up there, but that's way beyond what you need to reconcile the synchrotron. The other numbers basically limit you to something like 10 to the 5. So you're 3 orders of magnitude too high. So there's something broken when you try to do this. And you can think of this another way, which is if you try to pack this quiescent gamma ray emission into this region that's about 7 gravitational radii, you would end up with an opacity to pair production that's almost 100%. So one of the big questions, of course, is if you start to stratify these regions, can you get around some of these constraints? But that's something that we'll be exploring in the future. And so what we did in this paper was we really just took these 2 heuristic models, one representing the region at the base of the jets, and try to see how far we could go in terms of fitting that region consistent with the constraints we have on optical depth from synchrotron self-absorption, but also fitting the high energy. And we found that we really couldn't fit the gamma rays consistently for the arguments more or less that I mentioned. And then if we go further out to look at regions that are explored by, thousands or, 600 to 1,000 gravitational radii, we can fit the high energy fairly easily, but then of course we're going to be lower than the radio. And so what does this mean? It means, not too surprisingly, M87 seems to be stratified, but it can't be fit by one of these types of single zone models. Here are just the parameters, and this shows you from the models that these are basically the numbers we got from very order of magnitude, milligauss, sort of on the order of, few Gauss fields, in this case, 10 to the 5 density. And you're near equipartition, near the base, but then you have to go really out of equipartition to create the gamma rays. And this creates quite a lot of problems. So this is discussed in the paper. And now what we're trying to do with our group and many other groups is make a spectrum where we can actually fit the entire spectrum based on these underlying models that we talked about. So you can expect quite a lot of work. But what I think is going to be interesting is trying to put this into perspective with the flaring and the past. Are we catching M87 at a typical time? What happens? Is there maybe a special dissipation region that appears later that can be revealed by variability? And that's why we need to start thinking about the time series. And so this is just to show you light curves from the optical UV going back to the year 2000 and from Chandra going back to the year 2000. And you can see that around 2005, 2006, there was quite a lot of activity in the nucleus of M87 as well as the nearest blob, this knot called HST1. And the same goes for Chandra. There was this really bright variability in HST1, and the nucleus was brighter as well. And these little blips here are basically gamma ray flares. So there was very fast gamma ray flaring at this time. But now, where we're over here, both the nucleus and the core are very quiet. In fact, HST1 is much subdominant compared to the core, which is great because that spectrum that we have really is showing us exactly the output from the base of the jets, more or less, or the inner, the inner jets or accretion flow, and the gamma rays were quite steady. But what happens next in the future? Will we ever come back to this point? And so we have to keep looking. And in fact, in 2018, we know that we caught more variability than in 2017. So that's something we're actively working on, both within EHT, but also for the future campaigns from the the theory group and for all the multi-wavelength we have as well. So you can stay tuned for that. And hopefully by comparing these two snapshots, we'll start to be able to limit some of these models. So this is getting into moving in a little bit forward towards the ngEHT aspects of my talk, which is that we really want to be able to make movies to understand the variability. I like the way that Silke, I think, brought it up in her talk, that we have so much different kinds of variability from the AGN point of view, this sort of deterministic things, maybe periodic types of signals that are being driven by things happening near the accretion flows in the inner region that we see with EHT, but then also there can be a lot of stochastic processes, and trying to pick these things apart will help us break down some of this degeneracy. And this is just a movie. You saw Elliot had shown a simulation for this sort of tilted choke jet where you got some interesting sort of carving out some regions when you look down on the flow. In this case, we're seeing flux eruptions from the MAD inflow, and these basically plasma that's magnetically, very, very magnetically dominated. And it can actually be visible in your images, but For EHT, maybe it gets blurred out quite a bit. For ngEHT, we'll be able to likely see these signals at the horizon, but we're also interested in the consequences it's going to have further out in the jet. And the reason I say this is because we know this happens in X-ray binaries. And I just want to bring this up. I know X-ray binaries aren't totally the theme here, but they're very...
5 minutes, please.
Sorry?
5 minutes.
5 minutes, okay. So basically, X-ray binaries are extremely interesting sources, as we've heard before from Rob and from Alex's talks. And this is the spectrum of an X-ray binary. What you're seeing is basically X-rays coming from very close to the black hole, and the infrared, this is all the jet, is basically synchrotron emission. And so if you have noise variability that's coming from something interesting happening near the black hole, you would expect that it would be carried forward perhaps into the jets, depending on how coherent these structures are, with some sort of lag. And it turns out that's exactly what we're seeing. It's a pretty new field because it depends on having very fast optical and IR timing. But we're finding correlated, basically broadband noise that the infrared regions lag the X-rays by something like hundreds of milliseconds, which means that you're talking about distances of pretty large, 10 to the 3, 10 to the 4 gravitational radii, where vibrations that are obviously being driven by something near the black hole are being carried forward. And we found this now in several different X-ray binaries. So I think this is a pretty robust feature, and this is very likely to scale to the types of low luminosity AGN we're looking at with EHT. What's really amazing is that we've actually seen harmonics of these, this is power spectra in the X-ray, and you can see these peaks here are these quasi-periodic oscillations. These type C oscillations are usually associated with jets, and here for the very first time it was seen 10 to the 3, 10 to the 4 gravitational radii further. So that's just amazing. It means, these magnetic field lines are effectively like heartstrings, being plucked somewhere down near the black hole and vibrating further out. And so if we can start to look for this and understand this, for instance, also in AGN, then I think that there's a lot of possibility for eventually using non-horizon observations further out in the jets to be able to diagnose what's happening closer in. And so there's a lot of crosstalk between the X-ray binary and the AGN community on this, but this helps guide our thinking about the kinds of observations that we need to do. Now, I won't say too much about this, but Sagittarius A star, of course, is our sort of poster child for really these stochastic vibrations. And this gives you a sense of what we can do with the multi-wavelength. Now, the EHT observations aren't out yet, but they've really helped guide our thinking. And these are some work that, again, Kaushik will hopefully be mentioning a bit, but he's been looking at modeling multi-wavelength spectra. And we have tons of information also during our campaigns now, but also from 20 years of monitoring from the radio all the way up to the X-ray. And I won't go into the details here, but the point is that in the X-ray, we have basically daily flares, and we have enough of these over the past decades that we can make cumulative distribution functions and power spectra and try to understand how they vary. And also we can do the same thing in the infrared. And so beyond just trying to fit the spectra and also to try to explain the variance that we see in each band with our simulations, you could do things like make fake light curves in the different bands and actually treat them the same way the data are treated and compare them to cumulative distribution functions, which are really incredible probes, getting away from just a single flare where you don't really do much but sample this stochastic distribution. You can actually start to compare to the whole family of flares. And so this is the data for the CDS for infrared in the black. And you can see with the simulations, we're not quite there, but in some simulations, like these are more strong field, we have more or less the right kind of cutoff, but we're getting too much lights, too many bright flares. And then on the other hand, these weak types of magnetic field simulations are maybe under predicting the variability and the amount of light that we get at these lower flux rates. And this can really help us. And one of the questions is, when we improve the resolution of these simulations, will we start to probe these scales better? Or, is it, as Sasha was saying, that we're really pushing on the edge of what MHD can tell us? And so I won't say the details, you've seen this plot several times, but I just want to make the point that as we push to higher resolution and start to do resolution studies of this together with the light, this is being led by many of these younger people, we'll get better information about the multi-wavelength. The multi-wavelength will feedback to give us better information about the processes that are lighting up the particles, and we can maybe rule out different models. And some of these plasmoids seem to be kicked up along this interface region. We've heard from George about these questions along here about, maybe having also entrainment coming a little bit further on and how you mass load the jets. And it's funny because Koshik worked on this last year, which we thought at the time was a very high resolution simulation, but now it looks pretty fuzzy compared to what's being done. But if we could focus more resolution on these parts of the jets, I think we can start to see if certain types of regions light up preferentially and can maybe address this question of where particles might be dissipated more preferentially during flares. Is it really near the black hole, or is there something special happening further out? I'll skip over this. I just want to, yeah, I'm almost done. I just want to skip over the fact that, Matt Lister will talk more about these AGN monitoring, but there's a lot that we can learn. We see campaigns that last, for like months. And I think with the ngEHT, to really capture all this physics, what we need to do is keep in mind that we have, things like the Vera Rubin Observatory, ngVLA, SgrA, and CTA, and we want to have very dense campaigns. I won't mention this twinning, but you can ask me about that. I think this would be very beneficial to us. And we have to think about dynamical scheduling. So Matt will say more about these kinds of campaigns, but it's not like we're starting from scratch. We understand the types of information and the pacing and the steps that we need to do. And then we need to think about staging the results, calibrating them from these horizon sources to the point where maybe we can identify what's going on near the black hole just by looking at the outer jets in the non-horizon sources once we've calibrated these variabilities based on dense campaigns. And so I just want to say one thing about CTA. This is an amazing facility that will be online. It's the next generation high energy gamma ray facility. And one thing to point out is that on our timescales for flares, it's about 5 to 6 orders of magnitude more sensitive than Fermi. And its KSPs are very similar to what we're interested in. So we should be talking already with CTA and these other facilities to line up our observing plans. And I think the challenge for the models we've been hearing about so far is going beyond electron physics and also moving into proton acceleration, because then we can start to think about how what we do with ngEHT together with multi-wavelength fitting might also lead to neutrino predictions. So I'll leave up my conclusions here, but these are sort of the main punchlines. And I think that there's incredible capabilities coming and we need to take advantage of them, but we also need to think ahead, especially about how we're going to allow certain observing modes if we want to get the most out of our models. Thank you.
Thanks very much, Sarah. We have a few minutes for questions. So please raise your hand or. Okay, maybe I'll get us started off. It was very intriguing, the connection between the X-ray variability and the infrared variability of the X-ray binaries. That obviously could be explained by the jet. Is it also consistent with the corona just being some atmosphere to the inner accretion disk?
You mean the infrared light?
Yeah, for X-ray, you said for X-ray binaries, there was a very good correlation with the time delay between the variations in infrared.
No, these infrared observations are highly polarized as well. And it's very well understood that actually the infrared is coming from, that lag is way too long to be coming from the corona, because you don't expect the corona to be 10 to the 3, 10 to the 4 gravitational radii as well. But also the polarization tells you that you're looking at the jets in these sources.
Right. But how about the X-rays? Can the X-rays be? Oh
yeah, no, the X-rays is probably coming from, whatever you want to call the corona, whether that's the inner accretion disk or the base of the jets. But in terms of the timing, it's definitely down there, more or less what we would call the EHT region of interest, right, in a supermassive black hole.
Okay, I see we have a chat. Avery has a question.
Hi, Sarah. So
Hi,
Avery. I'm very happy to see variability is now rising to the top as a key science observable. I'm, as you can imagine, even happier to see so many what I might call hotspots appearing in these simulations. But one thing I worry about, especially at the jet wind interface, is that a lot of the focus there has been driven by electron heating prescriptions that are in some cases quite ad hoc. It's really, we have large magnetic fields and still have some density, and some. We heard the talk this morning and the talks yesterday. It's becoming ever more secure, but maybe hand wavy justification for that. So I was just curious what you're feeling about how much would you bet that we're really dominated by the funnel region emission, and it's really these plasmoids that are being generated with the interaction of the fast jet and the slower wind.
So I would not bet my salary on anything right now, because I think that, as you say, there's a lot of questions, and this is really the point of exploration that we're just starting. I mean, we've heard about this from some of the other groups. I think one of the keys will be to increasingly move to focus, simulations, as Sasha Filipov was discussing, on smaller scale regions with, for instance, GR, PIC MHD, and so on, to start improving the models. I don't know if it has to be plasmoids necessarily. You could get a lot of this acceleration also just from Kelvin-Helmholtz, instabilities, and there's quite a lot of different models about this. The key point is, for me, that each one of these different scenarios will have predictions that will differ from each other in terms of their, the stochastic predictions, the distribution of the flares and the light and the spectra. And if you put all that together, that gives you a target to start to maybe be able to discern between these models. I mean, that's been the way that the AGN community has been looking at this for quite a long time with those campaigns. And hopefully Matt will talk more about this in the next talk, but they have been looking, for instance, for polarization swings together with certain types of variability, but they just don't have the sampling to even tell. The current models that are sort of in the running now are turbulent acceleration versus, reconnection, for instance. And the potential is there to tell the difference between these. So that's the way I'd like to think of this, is that this is going to be observationally driven to some extent. With Sagittarius Star, we're already seeing that whether it's resolution or something else, we're not quite getting there with the prescriptions we're looking at. But, as you well know, I think we're pretty far from exploring that parameter space.
Okay, thanks very much, Sarah. We have to move on to the next talk, but we very much appreciate the great talk that you just gave. And any further questions we can ask during the discussion period. Okay, our next speaker is Professor Matt Lister from the Department of Physics and Astronomy at Purdue University. Matt got his PhD at Boston University working with me, I'm happy to say. And he is now the leader, and has been for a number of years, the leader of the Mojave VLBI survey. So Matt will tell us about multi-frequency active galactic nuclei monitoring programs and the next generation ngEHT.
Okay, thanks, Al. And thanks to the organizers for inviting me to give this talk. My goal today is to convince you that AGN monitoring should be a key concept in the ngEHT science case. So I'm going to break this down into 3 subtopics here. I'll give you a brief overview of what the global endeavor is right now for multi-frequency AGN monitoring, what science contributions ngEHT can make, and then I'll talk about some viable targets for that monitoring. So there's been a huge, I guess, vast volumes of literature on multi-wavelength monitoring. Just a little aside here, everyone calls it multi-wavelength monitoring, even though the title of my talk is multi-frequency. No one ever plots wavelength on an SED, but that's just historical precedent. So I'll call it multi-wavelength monitoring for the rest of the talk. But at any rate, what the key goal here is to look at the flaring behavior of these AGNs as a function of frequency. And that gives you the keys to understanding where and how the high energy photons are being produced. And that's the main goal here. And the big takeaway in a SED like 3C279, which is a highly variable blazar, is that as you go up in photon energy, you're looking at much faster and more significant flaring activity. And by the time you get to TeV energies, you're talking about flux doubling times that can be on the minute time scale. So the focus of this talk is the radio regime, which is actually the least variable, but it's perhaps one of the most important because it's the only one where we can get structural jet variability information. And just a little aside here, we've been talking about time domain astronomy. Time domain astronomy really began with AGN jets because these are the most variable long-term broadband phenomena. So there's a long history involved in that. And so we're precursors for the time domain era. So there's two main modes at which multi-wavelength monitoring happens. The first are what Sarah was talking about, the scheduled campaigns, where you've got the targets coordinated well in advance. You've got the observation window. This involves a huge amount of effort from people around the world, where you have to send individual proposals, get them approved. Some examples would be the ngEHT campaigns on M87, the 12-year cycle of OJ2D7. There's been campaigns organized around that as well, and many others. The second mode is essentially following alerts, so TOO or triggered campaigns. And those alerts come from facilities that do all-sky monitoring, like Fermi, or sometimes you get an alert from one of the well-studied blazars. So there's a few dozen of those that are monitored quite frequently. What happens if after the alert really depends on how the community feels about it. So if it's something super exciting, then you get this sort of ad hoc response where lots of people start to observe it. One example, a famous one, would be the neutrino detection by IceCube and the detection of TXS 0506. Another would be a TD event in Swift J1644, but there's other examples as well. So apologies about this slide. There's a lot of information on here. I will direct you to this website here if you're interested in the list of monitoring programs, past and present. There's a huge range of observing cadence, how frequently the sources are observed, how much of the sky they cover, and down to what limiting flux. The radio is well covered. So we've got the OVRO survey, which will soon be looking at 5,000 blazars on a weekly basis. Radio loud compact radio sources. And there's also VLBI surveys, which I'll talk a bit about today. In the optical, as Sarah mentioned, Vera Rubin is really going to revolutionize this. But there's also many ground-based telescope programs. And we also have to include the exoplanet missions as well. They're low sky survey coverage. They're looking at a narrow range of sky, but they give you excellent light curves. SgrA is probably the poorest regime. There's nothing really planned here. Swift does have the BAT monitor, but it only looks at the brightest AGNs and X-rays. Gamma ray is well covered by Fermi and the air shower telescopes, including CTA, that again, Sarah mentioned. And then we've got neutrino monitoring as well for the multi-messenger component. So there's a number of facilities that will hopefully still be running. We hope Fermi and Swift will still be going by the time ngEHT comes around, which will provide these alerts that we can look and follow up with ngEHT. So what about the role of to play in science? Okay, so let's start talking about with the variability aspects in the radio. So the majority of radio loud AGN actually are only mildly variable at radio frequencies. You tend to have these very long duration flares that are a few percent of the quiescent level. So it's really the core dominated blazars that show you these massive departures. And that's because they're highly affected by relativistic beaming. And so those beaming effects, they compress the time scales of the flares and they amplify them as well. So you can get a factor of 10 increase in flux in a single flare. And if you observe over a decade or more, so this is actually a 20-year light curve for these three AGN here. Here's a very rapidly varying AGN 0235 plus 164. That can vary by a max range of about 30 or so at gigahertz frequencies. And when you have these big flares, there's often an ejection of a new Parsec scale jet feature that we can look at with VLBI. So there's two main advantages to submillimeter VLBI, which we've talked about a bit at this meeting. The first is the reduced source opacity. So when you go to high frequency, you're probing down near the jet base where supposedly all of the high energy photons are coming. So that's the highest energy region in the jet. It makes sense that the high energy photons are being produced there. You also end up with far less Faraday rotation effects and depolarization effects. And the killer app is obviously higher angular resolution. And that also improves your polarization imaging because you get less beam depolarization, the blending of features that have orthogonal electric vectors. You can resolve the jets in the transverse direction as we've seen in M87 and some other nearby radio galaxy jets. As I'll mention in a little bit, you can track the ejections down much closer to the base, and so get their timing much better, and then follow their trajectories so you can get their kinematics. The challenges, though, with submillimeter VLBI monitoring are achieving regularly spaced long-term coverage. So the current EHT observes only in short duration seasons, once every year or twice a year. So that really constrains what type of science you can do if you want to get regular long-term coverage. So that's an issue that has to be addressed with ngEHT. So also the fact that the spectrum of the jet is fairly steep. So as you go further downstream, you're into a low brightness temperature regime, and that makes it much more difficult to image. You also want to be able to sample the beam well with terms of pixels across the beam. And so if you want to create a large image, that's computationally very intensive. And then the overall aspects of how you do VLBI, it's difficult to do, say, a lot of sources per day compared to something like Vera Rubin, where you get millions of sources per day. You're certainly not going to get that in with millimeter VLBI monitoring. So there's three main types of jet that you can see with VLBI. The first are these young radio sources, sometimes called compact symmetric sources. And they typically have jets that are a few hundred parsecs. They've been recently turned on. They don't change very much over time, so they're not great targets for monitoring. Radio galaxies like M87 are better because you can resolve them transversely. They're relatively nearby. But again, their speeds are quite slow, and then their jets really fall off in brightness temperature as you go downstream. Blazars are a very common VLBI target because they're so compact due to relativistic beaming, and there's a huge overlap with what Fermi sees. So nearly every single source that Fermi sees is one of these blazars. One thing you can do is look at the long-term radio monitoring light curves, something that's been done by the OVRO, Owens Valley program. And what you see in the radio light curves is really indicative of what's going on parsec scales. So for example, this young radio galaxy here's an image of the VLBA in 2017. If I were to show you another one in 2000, it would look almost perfectly identical to that, because things change extremely slowly for these guys. So less than 22 microarc seconds per year. Now, by contrast, if you look at a nearby core-dominated jet like 3C120 that's affected by beaming, you get an enormously rich light curve with a lot of structural activity. So in 3C120, I'll show you an animation in a little bit. The features move downstream at 8 microarc seconds per day. So that's pretty impressive, and doesn't mean it means you don't have to monitor it for very long to see a lot of changes with ngEHT. You can do a survey, which we've done with Mojave, of jet speeds, and you find most of them are in the sort of 100 microarc second per year range, but there are a small cohort with very, very fast jet speeds. So these are obviously of interest for short-term high resolution monitoring. And the key here is when you do the VLBI imaging at millimeter wavelengths, you're looking at the regions very close to the jet base. And that, again, is where the high energy emission is supposedly coming from. You can get information on the compactness, the activity level, the polarization state. Jose Luis Gomez gave a very nice talk on this the other day. There's also a great annual review article by Bia Bocardi on this subject as well. One of the big concerns is whether this core that we see is actually just a recollimation shock downstream. That's predicted by hydrodynamic models. And when features might go through that recollimation shock, you might expect to see some behavior at other wavelengths, like, for example, rotations of the electric vector position angle in the optical. And there's been various programs which have looked at that as well. You can also look at downstream at features. So M87 is a great example because you can see there's a fast spine and a slower sheath. And so you can get a whole velocity field type of analysis there. For further, just for jets that are a little further away, there's still an issue of finding when the features were ejected. So here's some work from the Boston U group, where you can see there's acceleration going on near the core. And so that means to get the ejection date, you have to extrapolate that acceleration. So there's an uncertainty about when the feature was emerged. So if you can image this region, you can get the dates of those emergences and compare them to high energy flare events much more accurately. And then angular resolution gives you this ability to resolve individual filaments. Again, M87 is super close by. Imagine being able to do that for much further away jets. So there's a lot of science that can be done there. In the Mojave program, we've also seen evidence of these swings in the jet position angle over time, decadal type timescales. This is 15 years of this source here. There's something that looks tantalizingly periodic. There's not really enough cycles here to really say nail that down. But we're talking, in the case of OJ287, tens of degrees in only a few years swing. So the easiest way to do that is to have some sort of substructure within a broader flow that's being energized, not moving the entire jet back and forth, because that's an enormous shift in a short amount of time. So that's one aspect you can do with high angular resolution. Another is to do polarization mapping, which we've started with the VLBA program to do between 15 and 43 gigahertz. And you can see here the evolution of the rotation measure as you go forward. We're doing this monthly. So there's lots of dynamical effects you can see both in structural and polarization. That would be fantastic to do with ngEHT. Okay, so what about the targets? So one of the targets that have been suggested that have been very exciting in terms of resolving the regions very close to the black hole are these nearby radio galaxies, and Neil talked about that in his presentation. So within 50 megaparsecs, these things tend to be very weak. They're at the few millijansky level, which makes them challenging to look at, but the spatial resolution you can get is fantastic. So if you want to look at these, you really need sensitive array with lots of dishes. If you go out a little bit further, the 100 megaparsec range, then you're starting to probe more massive black holes that are more powerful and compact, things like 3C84. NGC 1052 is a nice example, which is ejecting features in both the main jet and the counter jet that you can study. This is the VLBA study at 15 gigahertz with Mojave. So doing the counter jet is very interesting because you can, excuse me, nail down the viewing angle to a much higher degree of accuracy. And you can look at the velocity fields on both sides of the core. But the main targets that are the easiest ones to observe are going to be these radio bite blazars. So they have very compact cores, which is great because you can self-calibrate. There's enough emission there to do polarization imaging and direct fringe detection. And these have the largest overlap with the multi-wavelength programs. The reason for that is that their SEDs are jet dominated and they're highly beamed, so you get a lot of activity. And you don't have to worry about trying to model all the host galaxy and accretion disk emission because the jet is just dominating everything. In the case of 3C120, you can see there's a lot of activity that happens very rapidly, so that's great for making movies. But the downside is that because they're much further away, you get poor spatial resolution. So this number here tends to converge to around 1/4 of a parsec once you get redshift 1 and beyond. So we're not talking black hole horizons here. We're talking well downstream. And there's also larger projection effects because these jets are coming at you within degrees of the line of sight. So the name of the game in millimeter VLBI is brightness temperature, and it's something you really have to consider when you're looking at targets. The brightness temperature is just a function of the flux density, your observing wavelength, and the size of the emitting region. But if you want to think about the maximum angular resolution you can get, it's a function of your observing frequency or wavelength here and the maximum baseline. So for a ground array, taking into account a fringe detection limit of somewhere between 10 and 100 millijanskis, you need to be looking at things that are fairly high brightness temperature, quite compact. And a lot of the radio galaxy jets just aren't going to cut. So you're not going to detect those on the longest baselines. And that's really kind of takes away the whole purpose of the ngEHT. So again, you're going to have to push this number down if you really want the angular resolution on these low surface brightness radio galaxy jets. Now, the flip side is that some of these blazar jets are quite compact. And for that, you can see that wavelength doesn't really help you. You need to go to larger baselines if you want to study those very compact regions. So how many of these are there? And it turns out there are quite a lot of compact blazars, and we know almost exactly how many. Leonid Petrov has put together a very nice catalog, the Radio Fundamental Catalog, and it's complete down to 200 millijanskis. So what you're seeing here is a log N log S plot where it's showing you the cumulative distribution. So you can see the numbers drop quite a bit when you get to the high fluxes. This is effectively a single epoch survey. Remember, these things are quite variable. With Mojave, we've done a multi-epoch survey. So what you're seeing here is a plot of every blazar that has exceeded 1.5 Janskis over a 25-year period. And there's left, if you take 1 Jansky as a fiducial point, there's roughly about 600. And at any given time, about maybe half of those are above Jansky. So there's a lot of targets there that are compact enough to do millimeter VLBI on. The brightness temperature distribution also indicates that as well. Over here is the flux limited sample for Mojave, and you can see that the peak is close to 10 to the 12. Okay, so that will give you enough compact flux to do fringe detection on.
5 minutes, Matt.
Oh, thanks, Al. And really, again, if you want to probe this small population out here, you have to go to space. So we've done that to some extent with Radio Astron already. The Radio Astron survey looked at around 200 of these compact AGN, and very impressive fringe detection statistics. So even up to 25 Earth diameter baselines. So you can see here, this is 1.4 gigahertz, 5 gigahertz, and 23 gigahertz. The sensitivity of the receivers goes down as you go up in frequency, so that affects things, but also the number of sources that are sufficiently compact goes down as well. So you can see at 22 gigahertz, you got about 30%, but that's still pretty good because Radio Astron, it's a fairly large spacecraft, but it's certainly not as sensitive as a ground-based instrument. So there's lots of great targets, but one of the problems with space VLBI monitoring, again, is that changing UV coverage. So to make animations and movies, you really want to keep that the same between epochs. So that's going to be a challenge planning that type of mission. Okay, so in summary then, time domain astronomy is really going to take off when Vera Rubin launches, because we're going to have light curves in the optical, and people pay a lot of attention to optical monitoring. So that's really going to up the visibility of AGN science, among other things. And I hope I've shown you that these compact blazars are going to be a primary target for ngEHT monitoring. And I just want to make a case here that the ngEHT will provide exclusive imaging data that no other facility will be able to provide on activity at the smallest scales. And so that's critical for understanding jet launching and acceleration. And we really need to emphasize the synergy with the multi-messenger and high energy photon facility. Okay, so I'll stop there and take any questions.
Thanks very much, Matt, for a very comprehensive talk on the topic. If you'd like to ask a question, please either raise your hand or let us know by chat that you'd like to ask a question. LOC, I don't see any raised hands yet. Let me ask the first question.
Looks like Thomas has a question, actually.
Oh, okay, good.
Hi, Matt. Thanks for the nice talk. I'm completely on your side, and I agree with everything what you say. There is one possible limitation which has to do with the brightness temperature versus frequency. It appears that if you plot the brightness temperature versus frequency for many AGN, somehow you go down in brightness temperature as you go higher and higher in frequency. It could be that the brightest temperature peak is somewhere around 22, 43 gigahertz. At 86 gigahertz, we have already a factor of 3 or 4 lower brightness temperatures, and 22 and 230 gigahertz, maybe even lower. That practically means that we are resolving out most of the jet emission. Do you think that could be a killer? That at the very high frequencies, the sources are not just not compact enough anymore?
Yeah, I mean, the radio astron statistics do suggest that possibility. And I think we're going to have some more comprehensive ground surveys. There has, as you know, at 86 gigahertz, we're sort of at the 100 source level. But I think that's going to have to be expanded to really get good statistics on it. I think it also underlines the idea that you want to have at least a few very sensitive ground elements in the EHT. I know it's difficult to improve on ALMA, but having one baseline to a very sensitive telescope really opens up the possibility of looking at lower brightness temperature objects.
Yeah, that's completely right. I mean, the most important point is to gain sensitivity as much as you can. And that's maybe more important than gain UV coverage. So having at least a 1 or 2 good high sensitive reference station, 100-meter class telescopes or bigger, will certainly help for the ngEHT to do all this kind of science better.
Yeah, Svetlana Jorstad has her hand raised.
Hi, Matt. Very nice talk. Thank you very much. So to measure apparent speed with ngEHT, what do you think should be a cadence of observations?
Yeah, so it depends on the source. So something like 3C120, where you're getting micro-arc seconds per day, you're going to have to observe that daily. Whereas some of these radio galaxies and the young radio sources, you could get away with observing those every few months.
Okay, but how do you think will be able to identify components or disturbance which we see very close to the black hole with those which we see on?
Yeah, so you don't want the features to move appreciably between the frames effectively. So our experience with the Mojave program is it's typically, if you're moving more than a resolution beam width, then things get difficult. That's also the case even if you try one of these wavelet type analysis that Mertens did with M87. So the rule of thumb is whatever your angular resolution is, you want to make sure that your angular speed is less or a little higher than that. So you're not moving through an angular resolution element between the frames. So
in general, for each source in this case, we need to know some kind of apparent speed from longer wavelengths to do proper observations with ngEHT.
Yeah, and another way to do it is to have two, shortly spaced. You can do a test, right, where you have 2 good data quality EHT images taken a day apart or a few days apart, and do a difference image on them. And if they look the same, then you're golden, right? You can up your cadence or make your frequency of observation a bit less. So that's one easy way of testing. You observe frequently at the start, and then if it doesn't look like there's much change, then you back off.
But this is very expensive, I think.
It will be for the fainter sources, yeah. For the brighter ones, you could get away with not having a full UV coverage.
Okay, thank you.
Okay, I have. I'll ask a question here, I think, or somebody else has. Let's see.
It was me, Alan. Go ahead.
Okay. Yeah. Well, I was just going to say that it sounds like since we might be able to see the incipient features moving down the jet, that probably want to select sources in a dynamic way, so that I wonder if you would agree with that. So that you are monitoring and gamma ray, monitoring and radio and so on, and then decide on your source list every day based on what was happening the day before. Would you agree with that kind of strategy?
Yeah, it's a tough one because you don't want to bias yourself into this idea that, oh, okay, the radio flare is going to happen, or the radio ejection is going to happen after the gamma ray flare, right? So you want to be able to look at both possibilities, that yes, we were observing in VLBI before the flare happened or before the neutrino event happened.
Yeah.
So I think you're going to need some combination of regularly monitored jets that you think are going to be neutrino emitters or TeV flare emitters, and then another set where it's more of a, a general, we're going to observe these at a regular cadence.
Okay, thanks. So Thomas, you had a question?
Just a comment. I mean, we have seen in the case of 3C279 that the source does change on a timescale of a few days. So we are talking about structural variability with micro arc seconds per day motion. And I think what is needed is you have this long-term monitoring, which is not so expensive, which could be done with other instruments, but there should be some sort of burst mode when a source comes really into action, to have a really high cadence, a few day time scale monitoring. I'd just like to remind you that in the published 3C279 kinematics, we basically see extremely rapid motion from one day to the next. And of course, we cannot monitor with the ngEHT 365 days per year. So we have to identify those timescales where such monitoring makes sense, which is at the onset of the flare and in the rising phase, I think.
Okay, thanks very much. Let's thank Matt again, and then we'll move on to the discussion period. It'll be led by Dr. Haggard, Daryl Haggard.
Thanks, Alan. It's a pleasure. Thanks, everybody. I'm going to put up a slide and remind you all the talks we heard this morning to kick off the discussion. But since we've all been sitting a lot, if anybody wants to use my little brief introductory thing to just stretch or do whatever, please do that. So I'm going to, yes, Alan is on my same page. Okay, so let me just remind you of all of the fantastic talks that we've heard this morning. So this is graciously made by Britt, one of our LOC members, this lovely sort of summary of our morning. So we started off really talking about sort of the state of the art of simulations. We heard about plasmas from Sasha Filippov and some additional modeling, GR-MHD kind of modeling from Andrew Chale and George Wong. And then we dove in for the second session of the morning, hearing a lot about multi-wavelength and some multi-messenger and some sort of strategic monitoring of AGN of supermassive black holes from Sarah Markoff and from Matt Lister. So thank you. Maybe you can all join me in clapping your hands, thanking all of our fantastic speakers this morning. It was really a fantastic morning. The discussion has been extremely active already today. So I feel like this is going to be the easiest job as a moderator ever. Since the conversations from the morning session spilled over into our coffee break because there was so much momentum in them, I'm hoping we can take our first few questions for our second two speakers, and then we'll just work our way back toward the theory talks this morning. So in particular, if people have comments that they want to share, there's been a very active Slack discussion about both dynamic scheduling and thinking about how to coordinate with multi-wavelength happening on the Slack channel. And Matt hasn't had too much time to engage with all of that yet because he just finished speaking. So I'd like to invite people to I'll stop sharing here at this point and just let us all see each other. Anybody who feels game and is not in their pajamas and wants to put on their screen their video, please do. And let me just invite questions or comments, or if any of the speakers want to grab something they thought was a really interesting discussion from the Slack or from the Zoom chat, please just grab that and let's highlight some of that conversation. Go ahead and raise your hand and we'll be able to see. Yes, Avery, go for it.
Hi, Daryl. So, one thing that has struck me with the recent tremendous evolution in simulation capability is that we often come across what looks like qualitatively new behaviors. So an example would be the decomposition of the accretion flow into these plasmoids. I think we've known for a while that it's a turbulent process, but the idea that it separates out into the string of pearls, seems like a fundamentally new and quite important thing. And so I'm curious what the people at the bleeding edge of the simulation enterprise think is the remaining systematic uncertainty. And when we build phenomenological models or parametrized models, what's the envelope that we need to be including in those to assure that we're going to be consistent, not just with the simulations that are done now, but the ones that will be done 10 years from now?
So just taking hands in turn, I'm going to assume, Sarah and George, that you're raising your hand to respond to Avery's question. If you have a different question, just say.
I had a different question,
Okay,
so
great.
wait for me.
Okay, great. George, go for it.
Yeah, so I'm just going to plug again the idea of viscosity. I think that we probably should look at viscosity and having viscosity in our simulations.
Can people respond without raising
Yeah,
hands or
Sasha,
waiting?
go for it. Yeah. Let's respond, have a natural conversation, and then I'll take Sarah's question next. Sasha, go ahead.
Okay. I mean, to me, the viscosity is the less important thing in this business. In particular, if you're wondering about reconnection, for example, in low beta plasma or something. I mean, viscosity in a collisionless plasma is sort of like in anisotropy of a pressure tensor or something. At high beta, this would be very important, but in magnetically arrested flows, viscosity, doesn't really do much, I think. So it really depends on what physical processes are we having in mind. And then we could have next questions about how we'll improve their modeling. So I don't think this question can be answered in, abstracting from physics. Let's talk about, reconnection or like those discharges or bird drizzles or something like that.
So I can't respond to the let's talk about it from the perspective of reconnection necessarily, but I think that, there were some disk simulations, unfortunately, I can't remember the citation now, that suggest that you have qualitatively, different time dependence behavior for simulations that were run with viscosity. And so this may be, only true necessarily for the same simulations. I know that ones I'm thinking of were run long enough ago that maybe they weren't, mad. But, if we're looking for, if we're thinking about what in the future we'll want to span the full parameter space, I think having simulations with different time-dependent features, that could be drastically different.
You have to remember that if you're putting explicit dissipation, you have to have resolution enough for the Reynolds numbers determined by the explicit viscosity to be higher than the numerical Reynolds numbers. So a typical resolution of 1000 cube may have a numerical Reynolds number of 10 to the 4, maybe a bit higher. So I think question of having explicit diffusion processes only makes sense for resolutions of a few thousands and higher. Otherwise, you'll be just measuring either numerical effects, or you're gonna measure, a honey which is stirred with a spoon, which is a very viscous, artificially very viscous fluid, or very resistive fluid.
Sure, but that's I mean, so I interpret what you say as that being a technical point versus I think the qualitative question of if you have a viscous, if you introduce viscosity into a flow, forgetting any of the simulation details, right? I would expect that the flow actually looks different.
Well, again, I'll argue that depends on what, like hydrodynamical turbulence, for example, doesn't care about the viscosity. It just truncates at the scale and there are no features associated with this viscosity. MHD turbulence is different because it has current sheets and they sort of, they're different. So.
Great, thanks everybody. All right, let's move on. Sarah, dive in with your question.
So yeah, this is also a bit for Sasha and maybe for some of Bart and whoever's here. But there's this disconnect, right, between, as you're saying in your work, that MHD is not really necessarily valid, and yet, we're using it, and it seems to be reasonably okay for the dynamics and the large scale stuff. But then we start to resolve these plasmoids, but of course, as you pointed out in your talk, the actual heating mechanisms and so on, isn't necessarily accurate. I guess the question that I have is, we've had examples in the past where you kludge something, the famous example being the alpha parameter, right, in the early accretion flow, and then you find out you're right for the wrong reasons, right, but then you eventually figure out what the right reasons are. And I'm wondering if we can manage that approach here as well. I mean, in the perfect world, we would do these simulations, from PIC up to the largest scales, but that's probably not going to be possible for a while. If we can make, let's say we run our very high resolution simulations with all the plasmoids and all the shear acceleration, everything you want that we could put in, and we manage to tweak things enough that we find out that some combination of these converged simulations, as far as we can tell, at or resistive MHD, and the prescriptions for lighting up the particles gives us the right, say, power spectra or something. Can we use that to back, maybe bootstrap is the word I'm looking for, our way to the actual physics? What do you think?
Well, if I'm answering, the question is really hard, I think, because as I guess, you're all finding that all of this electron temperature prescriptions are not exactly important for, let's say, the image, at least at the existing resolution. So I don't think this, based on that, I don't think it's a constraining, you cannot constrain plasma physics from the image, it seems, right now. And maybe you'll not be able for 10 more years or something. The multi-wavelengths, I think, is more interesting because it may care more about where actual particle acceleration happens, what are the processes that power them, and what are the observed signatures. I think the image alone is just a poor diagnostics of plasma physics, at least now.
Right, but if we do think about the multi-wavelength, or even light curves in the millimeter band, if we can figure out what it takes on some level to get the right variability, I feel like that is a pretty strong diagnostic in some sense. But then, how would that be fed back into the more fundamental simulations, I guess?
I guess what I'm finding really exciting is that with this 3000 cube HMR simulation, at least we can sort of semi-robustly look at these things. Like we can pin down on this and say, this is a current sheet, this is a shock if it's there, this is magnetized turbulence, this is something else. And now I can try to another plasma physicist could think about, what's the plasma physics that would give the right heating prescription. The previous problem is that the 200 cube, I don't think you can robustly identify any of the dissipative physics. It's all, as you say, is an alpha viscosity and it does the right job. So you don't see the microphysics. So I think that the progress will go, as I think Elliot also said, is that we'll see the right physics, the right size of interesting physics in MHD, and then we would think how to model them to first principles.
Great, thanks everybody. All right, Mohammed, please share your question.
I actually had a comment about the plasma stuff. I think people who have been trying to do these galaxy simulations, whether it's isolated galaxies or large cosmological simulations, have already encountered and thought quite a bit about these multi-scale problems. And I think the solution there that was to run these global simulations and find some regions in your global simulations where we have to apply prescription, and then go and do a very good job in understanding the physical mechanisms at these very small scales, and then incorporate them in these large simulations as a subgrid models. And I think, like, if you look at the separation of scales, like the RG in M87 is like 10 to the 14 centimeters, the plasma skin depth is like a few thousand centimeters. There's a huge separation of scales. You can't do the problem from first principle, but you can also use, as Sasha and many others talked about, you can't really trust what you get in in MHT simulations for like the dynamics of these emitting electrons. So if you want to really understand the dynamics of the matters that are actually responsible for these emitting electrons, you really need to do these subgrid modeling and then incorporate them in large scale simulations. So to me, I think this is a very promising way, and it's already been tried and successfully to some extent in other communities.
Well, the relevant community here is not the cosmological community, but the community that models Earth's magnetosphere and the solar wind, let's say. These are also plasma systems where the microscales are small and the large scales are large. The separation of scale is not as extreme as in black holes and neutron stars, for example, but it's out there. As I think I commented in the coffee discussion with George, is that it depends on the problem, really. Like if you're modeling how the solar wind blows out on the Earth's magnetosphere, there are very localized regions where the kinetic action of the kinetic physics actually happens. Like in the magnetotail, there is a reconnection. When the solar wind collides with the magnetosphere, there are also nice shock and the reconnection regions. There, people are like in the last 5 years are trying to put isolated like small peak simulations into those regions and see how this works. If you're thinking about interaction of the turbulent disk with a black hole, it's more challenging. I mean, there is no single place where kinetic physics.
So the advantage of doing this subgrid modeling is that you're not really thinking about a localized region. You're thinking about a phenomena that happens
let's talk about
everywhere.
subgrid models. I mean, if you're doing a subgrid model for a turbulent flow at the resolution of a 200 cube, all of your subgrid model will look like a numerical viscosity or numerical resistivity.
Yes. I mean, you have to do also a good job in the large.
So you have to do a really good job at the large scales before you can even talk about the subgrid models.
Or you can have a good imagination and imagine what kind of configuration for the plasma that you would end up with.
This has been really problematic for the field of the plasma physics. Like this is why.
And we can do that. We can do that after we have basically you creating a subgrid model based on a high resolution simulation. So you have a high resolution simulation and you average it over, a volume down to 200 cube, and you ask, what is my subgrid physics from the point of view of this low resolution simulation? And maybe indeed we will never have to run a high resolution simulation again, but first we need to run them.
Exactly.
Add the subgrid physics like you're suggesting, Mohammed, and like we're discussing. Maybe increase the resolution even further, because who knows what's next? Because we just increase the resolution by a factor of 10 compared to status quo, and suddenly we find all these plasmoids. Maybe there will be something else happening down there. So actually, that's something like, is there any ideas what's next? Because plasmoids were kind of anticipated, but is there something else that is anticipated at high resolutions? Are we done here? Do we need to increase the resolution even further to get completely new physics? Yeah, well, add new
physics. I mean, your models, like when you do like ideal MHT or two fluid, you're excluding some physics. But once you start going closer to the scales where these physics are important, you have to also add the physics. So
I think this
kind
is
of like
interesting.
The tail.
This is an interesting direction, and there are certain things to learn from the space physics community. The challenge is that they're not as easy usually to incorporate in relativistic simulations. Like even concepts of viscosity and resistivity are not as easy once you talk about general relativity. So yes, we need more complicated Ohm's laws. We better evolve two fluids. We better have anisotropic pressure tensor of electrons, have a subgrid closure for it. I think this is one of the interesting directions on top of very high resolution large scale simulations. Before that, I think we were just not ready for that, because at 200 cube, everything would look the same.
Can I ask a question about these very high resolution global simulations? At some point, what you're doing is you're just trying to supply the small scales with the proper boundary conditions that are informed by the global scales. But if you knew what those boundary conditions were, you could perform just a local shearing box type simulation and impose the right outer boundary. And so I wonder if it might not be more economical in the future to have suites of
shearing box simulations with a variety of informed outer boundary conditions that allow you to effectively run this hyper resolution, insanely large simulation, but local sense, and you can export it as your subgrid modeling to the lower resolution simulations that you could actually run en masse and produce accretion flows for a variety of different inputs, or jets for a variety of different inputs. So is there a future in which these sorts of local shearing box type simulations done with a variety of different boundary conditions could substitute for the single enormously expensive ultra high resolution global simulation?
I mean, the idea is like you get scale separation. So you have a current sheet and you have nothing around it, everything is smooth. And then you say, okay, well, that's what will be represented by our subgrid model, which you then try to get a traction on by running a shearing box simulation. But the problem that we're finding is that there is no such obvious scale separation. Basically everything is current sheets. Everywhere are current sheets. So like current sheets are close to each other. So it's a little bit hard for you to, without high resolution simulations, you wouldn't be able to even know how many current sheets are there. You see what I'm saying? So you have to, maybe eventually we'll be able to figure it out, but it seems like what you will have to do, you will have to make up the structure that is still macroscopic if you want to utilize 200 cube simulations.
I completely agree with Sasha. I think the problem is that, if you think about a shearing box, my first question is like, can shearing box become mad? Like MRI is not even interesting for this type of flow.
And it's not me who's saying that. So thank you, Sasha, for bringing that up.
So MRI is irrelevant for magnetically arrested flows. It's some sort of turbulence and magnetically dominated flow, but it's not MRI. So if you believe M87 is magnetically arrested, I don't think this is an interesting problem. It's a very interesting theoretical physics problem, but it's probably not super applicable to this type of flow.
Right, but so going back to something, see, the problem with having two Sashas is we don't know which one we're talking about. Sasha T is you said for a moment that you don't know how many current sheets you have within the grid cell because there's no clear scale separation. If there's no clear scale separation, then the default in astrophysics is it's all becomes self-similar, and at that point we should be able to integrate up over one of these grid cells in a way that depends only upon the bulk conditions within the grid cell and get your closure, right? So there's, I mean, that statement, it doesn't strike me as pessimistic, quite the opposite. It suggests that there is a subgrid closure that might be generic in that instance. The real problem I would have guessed would be if you might have a single small scale feature that is critically set by peculiar structures on global scales. Well, anyway, I mean, we could have a whole conference on this, I suppose.
Just a last comment on this. So the real problem in doing this small scale stuff is that the boundary conditions are dynamically in a non-trivial ways. So it's like once you even get these dynamically interesting regions from large scale simulations, just running the small scale simulations, if you run them with like the normal boundary condition, like just putting them back is a non-trivial problem. Anyways, this is for the future.
My impression, it only works if like the scales are really decoupled. Like in an Earth's magnetosphere, the plasma is entering into the current sheet and never comes back. It just sits in the current sheet forever. And there is no like the full feedback loop. Then you can do boundary conditions and it works. If the other way around, problematic.
Yeah, the current sheet feeds back into the surrounding medium, and it's just a nonlinear system. So because of this kind of feedback, I like, Avery, I really like your suggestion. You know, I agree it would be really nice to kind of find a way of approximating this magnetized turbulence on macroscopic level. It's just we're not there yet. We need these high resolution simulations precisely in order to establish what sort of model is reasonable and then calibrate it. And once we've done that, then sure, I'm happy to go back to 200 cubed and kill it. And I also really, I think Charles mentioned in the chat that using machine learning could be a good idea. And I guess what we might want to do is we might want to come up with some sort of baseline model that captures the basic kind of physics roughly for the subgrade model, and then fine tune it on top of that using machine learning. That's kind of what they do in cosmology. You need to take away the biggest trends and kind of fine tune the details. I think that would be a really cool way of moving forward.
Yeah, the problem is that if you take a 200 cube turbulence simulation and ask to predict what will happen at let's say 20,000 cube, I'm 100% sure no machine learning or neural network can predict the outcome, because it just doesn't know what will happen. It doesn't know the laws of physics. They're not there in 200 cube.
Can I just ask a question? Is it just blowing up, scaling up, or is there physics entering when going between the different scales? So is that the problem, that you don't know what kind of physics enters when going to larger scales between microscopic and macroscopic?
Well, we know the equations. They're not you know, even. I mean, there are Maxwell's equations and equations of motions for the particle. The easy example, I think, is the turbulence. Like, if you run magnetized turbulence at 200 cube, just the Reynolds number is small. So it's turbulent, but it's differently turbulent. You increase the Reynolds number, the current sheet starts to reconnect, and the whole thing starts to look different, and also at intermediate scales. Because the current sheet breaks into plasmoids, the plasmoids grow, and this already goes sort of back into smaller Ks. And before you actually push the Reynolds numbers to sufficiently large values, you cannot predict what will happen.
So you cannot grow the plasmoids larger, so they will change their shape.
At 200 cube, there are just no plasmoids. The instability doesn't have time to grow before it's erased away by diffusion. Once you increase the Reynolds number, the growth rate of the instability can compete. And it's not the only example. I mean, the problem is that, you know, we're talking about modeling electrons, but we don't really know what happens at resistive MHD level at sufficiently large Reynolds numbers. So we're trying sort of to kill both rabbits, but we don't really know neither of them.
Okay.
Well, on this topic of killing rabbits. All right, everyone, we've killed our discussion text section time. We have a couple of minutes left, but Avery has asked me to hand over the last minute or two of this session for a few announcements about signing up for the discussions tomorrow. So Avery, are you gonna take the torch for that one?
Sure, I can do that. So I just wanted to remind everybody to sign up for one of the discussion breakout groups for tomorrow. Your participation is critical to making that a success. There is a green line at the top. This is for somebody who's going to collate information, fill out a Google Sheets document with the answers to some very narrow and specified questions that we'll present at the very beginning tomorrow. And I've noted that nobody has signed up for the scribe position. So I encourage people to volunteer. In the absence of volunteers, a draft may be instituted. We will need someone to help collect all the excellent ideas people come up with. So I think Michael has posted the sign-up sheet link in the comments again, and I strongly encourage people to go and sign up and let us know that they would like to participate and how.
Looks like we've got a question. Go ahead.
Yes, this is Leonid. A question about this tomorrow discussion. Is that this quantization too small? There are several parallel discussion rooms, and each has on the same topic, but each has only 5, I think, places. So suppose that there are more than 5 people, and there will be then need to somehow collate output of discussions on the same topic in different groups. So it's too many hierarchical levels, I'm afraid. So why not to make them bigger?
So Leonid, this is a fantastic point. Not to bleed into describing in too much detail what's going to happen tomorrow. This idea of discussing in small groups where people can profitably discuss in an hour's time, then does have to be collated, and that is the purpose of the second morning session tomorrow, where all of the subgroups will collect together.